the crane stability based on the capacity. Now we will talk about the crane stability based on the COG. So there are three factors that should be considered in order to check the crane stability based on COG. First is crane COG during operational condition. This information should be clear at the beginning and will impact to the tipping angle and the ground bearing pressure calculation. So this COG we got by combining weight and COG from all components of the crane plus the load itself. And also we should consider if any slewing angle required during operation. So the second one is the tipping line and the tipping angle. Tipping line is a limit for the COG of the crane, so it will be not tipping during lifting operation. And the tipping angle is an angle that measure from the COG to the tipping line. Later I will explain about this. And the last one is the ground bearing pressure. Pressure. I think you all have familiar with this term. So the ground bearing pressure is the stress on the ground that caused by pressure from distribute from the crane to the ground. Now we are going to the crane COG stability. So as I have mentioned before, crane COG is calculated by combining the crane's component and the load itself during operation, right? So for the crane's load, here we will use the load to lift, which has been explained yesterday. So load to lift consists of the gross weight plus the rigging weight and hook and ribbing weight. But sometimes we also includes the dynamic factor to the calculation, so it will give more contingency to us for the ground bearing pressure. But in some condition, for example, if we use a suspended superlift counterweight, the load will be no longer realistic and lead us to unrealistic superlift requirement. And if we use an unrealistic superlift, maybe during operation it will be okay. But if it happens many times, it could damage our track of the crane or even the superlift connection to the cranes. So yeah, it will be better to use the without the dynamic factor in the calculation for me. We back again, and for the cranes deadload, you should refers to the cranes manufacturer. Usually they provide all the information about the components like boom, hook, and counterweight, and then the tracks and any other things. When we have when we purchase the crane, usually it comes with the manual for this crane. And it will be better if we could get the COG from them as well. Otherwise, we need to justify or estimate where the COG of each component is located. So for example, here just to showing what exactly I meant about how to calculate the COG. So in this picture, it is showing a crane with a complete component like boom here and tracks here, and then the counterweight here, car body is here, and mast is here, this one, and the other things. So I will use the center slew bearing as our origin point here. This is the center of the slew bearing, and this is our origin point to calculate the COG. And for the COG of each component, I will assume at the center of its component. So from that, we can measure the distance from component COG to the origin point. So let's say for example, the crane boom here, the distance to the center of the origin is L3. And then for the mass, I take the COG for the mass is I assume that it will be at the center of the mass. So the distance from COG of the mass to our origin point is L1. And for the counterweight, for example, the COG to the origin point is L2. So, and the load to lift here, the distance to the our origin point is L4. So everything, all the COGs will be measured to our origin point, and then combine all together to get the combined COG. And don't forget to put the load to lift into the calculation, right? So once we got the COG, then we could continue to the tipping angle calculation and the ground bearing pressure. And then uh, so this is the one we have talked about yesterday, which is showing how the load and slewing in certain angles can impact to the ground bearing pressure. As I've mentioned yesterday, the COG of crane usually in line with the boom direction, yeah. So when there is when there is a slewing at the boom, the COG will be moved to the same line as the boom direction. It depends on which load is dominant. Either it's the load to lift for the counterweight, or the uh, counterweight itself. So, for example, if the boom direction to here, then the counterweight will be at here, correct? Now the COG, so it must be on this line. It can be here or here. It depends on which load more dominance. Either it's the load in here or the counterweight itself. So and then the tracks where it's close to the COG will get the biggest pressure. So if there is no load at hook, so when for example, if the COG is here, then the more pressure will be getting by these tracks here. If the COG is at the rear, then the more pressure will be getting by this track. Correct. So that's the analogy to get the bearing pressure. And then if there is no load at the hook, then the COG only affected by the counterweight, and for sure the COG will be at the behind the crane. So if there is no load here, then the COG will be at the here. And for sure, the maximum bearing pressure will be here. But when the load is attached to the hook, the COG will start to move to the front, and then the biggest pressure now is at the front. It's probably here. So that's why how we get the bearing pressure. This figure or this picture I got from the Australian standard, if I'm not mistaken, but it is not mentioned how uh, the mechanism work in the book. So yeah, so I that's how why I explained the in the beginning. So actually, it is same like seesaw mechanism, if you know. Now let's see how seesaw works. Yeah, I will show you how the seesaw. Everybody knows seesaw, right? So if we have a seesaw here, let's say like this, we have 10 ton here, and then 20 ton here, and the distance is let's say here is 1 meter, and this is 2 meters. Now we want to get the COG. Where is the COG located? So we can combine that by using the total moment, if you know. So total moment here is, or we can use the formula like this. X equals uh, P1 times X1 plus P2 times X2 plus P3 if you have three loads, plus X3, and then divided by the total load. So we get 10 ton. We assume that it will be like this. The moment because of the 10 ton is like this, and then the 20 ton is like this, right? So 10 ton times 1 is 10 ton meters. 10 times, we will use minus here. Minus 20 by times 2 is 40 divided by 30. So it will be uh, 3. What then? The minus 20 by 20, 10 times, wait. Yeah. So it will be minus 20 times 2 meters, so it will be 40. 10 minus 40 is equals 30. Then we got the x is uh, minus 3 meters, correct? So the COG will be at the, no, it's 20 times 2. Yeah, the COG will be out of the here, somewhere here, correct? So the COG will be here at the right side, then the what you call this member will be rotating to this side, because the dominant forces is on the right side. Now, if we change this, become a track, for example, yeah, then this moment will acting to the here, to the track of, and then this, and then let's say this track will be sitting on the ground, right? And then the ground will give a pressure to counter the moment to here. And the more we get pressure will be at the front. It's right here. So that's how it works. So it basically it is same like a seesaw system, right? Now we continue with the uh yeah, this. And it will be the same situation with the outrigger here. The difference is how the mechanism to distribute the total weight to the foundation. So in this case, it's outrigger. The foundation is outrigger based on uh, the COG location. If the COG at the front of the crane center, then the most pressure will be at the front outriggers. And if the COG at the back, then the most pressure will be at the back. Now we will talk about the tipping line and tipping angle. So for crane with outriggers, the tipping line are lines which connected to all the outriggers point. So the tipping line of if we only use the outriggers, the tipping line will be here. Okay. And if the crane is working with the tire also, then we will have an additional tipping line to connect the tire point as well. So if we look at this picture, there is a tire in the system, then we have additional tipping line here. So the tipping area is this. But if it's only the outrigger, then it will be this, the green line, like that. As long as the COG is inside of the tipping line, then the crane should be safe during lifting slow. So if the COG is here, then it will be okay. But if the COG up from the tipping line, then we like for example, it's here, then we should rearrange to make it inside. So yeah, that's for the cranes without triggers. And the next one is a crane with a track or crawler. There are two types of track we see here. One is a track with a non-elevated sprocket here. For this type, the longitudinal tipping line will be drawn from the center of the sprocket here. And the other one is elevated sprocket here. And for this type, the longitudinal tipping line will be drawn from the edge of the track, which are touching the ground. So let's say it will be here. And for the transversal tipping line, we could take it based on the center to center of the tracks here. And then we continue with draw the tipping line, same as the crane outriggers, for example, like this. Then the tipping line will be at the center of here of the track, and then connecting to here. And that's for the tipping line. And the edge, the corner at here will be we need to see the what type of track we have in our crane. Either it's a non-elevated or elevated sprocket. So yeah, that's for the tipping line. Now we going into the tipping angle. Tipping angle is an angle that measure from the COG to the closest tipping point. for example, if you want to calculate the tipping angle for crane that using tire as a foundation, as shown here, if the COG located close to the front tipping point, then we will measure the tipping angle to the front tipping point here. That's the tipping angle. So for this, we could simply by using the tangent of horizontal distance divided by the vertical distance. So let's say the COG is here, and the distance to the front tipping line, front tipping point is 1 meter, and then the vertical distance is 1 meter, let's say 2 meters, right? So the tipping angle is uh, arc tangent of 1 meter divided by 2, like that. So what? Yeah. So that's how to calculate the tipping angle. But if the COG close to the rear tipping point, like this, then we will measure the tipping angle based on the rear tipping point, or is it like here. Then we will measure the tipping angle to the rear tipping point here, like that. So that's for the longitudinal section. And so on with the transversal section. We will measure the tipping angle according to where the COG located and which tipping point is closest to the COG. Like this, for this COG, for example, this is the center of the slurring, and the COG is at the right of the slurring. Then the tipping point the closest to the COG will be here. So we calculate the tipping angle based on this tip by reference to this tipping point, like that. So yeah, that's how to calculate the tipping angle. And now for the crawler crane, same concept we use here, the tipping angle to be calculated according to where the COG located. If the COG close to the front tipping point, then we should calculate the tipping angle based on the distance of the COG to the front tipping point. And so on to if the COG close to the rear tipping point, then we should reverse to we calculate the tipping angle uh, by referring to the rear tipping point. So yeah, that's for the crawler, and you need to be careful about the crawler's type, if it's non-elevated or elevated sprocket. And this one for the tracks for elevated sprocket. All right. So the tipping point is here and here. So beside the longitudinal section, don't forget to check the transversal also. So here actually it is mentioned that the tipping line of transversal section is at the outer connection between the tracks of the to the car body. However, we could just use the center here just to simplify the process of calculation, since it's more conservative. Now, the question is, if the COG higher, if we have the COG higher, will it be safer or not during the lifting? Is there anybody can answer this question? If our COG higher, is it safer or not during the operation? Let's say, for example, we have two
Well, the COG
COG.
higher.
Yeah, we have two COG here. One here, and the second is here. Which one is safer?
The higher is the most dangerous.
Yeah. So the higher is the more dangerous, correct? Because the higher COG we have, the smaller tilting angle we've got, correct? Now the other question is we know that we don't allow to having a tilting on the part line during lifting, correct? So for example, like this, we have crane like this. This is the boom, and the part line during lifting is like this. There is an angle here. Let's say it's beta. Is it allowed or not? So far, as I know, it's not allowed, right? Now
Not
the
all.
question, why does it not allow? Is there anyone know what is the reason?
Because the crane is for pulling, but for lifting, but not for pulling. So in that time, this angle is pulling. This is the means that not the manufacturer say, but the good practice. The meaning is we need to work less 5 degrees.
Correct. Yeah, that's the practically saying. So, practically saying that the tilting on the part line will create another additional moment to the crane's equilibrium. In the other word, we will saying that it will be uh, it will be there is additional moment here that created by this this projected forces because of the tilting. Uh, as we know that there will be additional projected horizontal load due to the tilting angle. And yeah, so it will create the additional moment. And engineering wise saying that the additional moment force will this projected forces will make the COG move higher than the original. So let's say the original COG is here, but because there is a additional horizontal forces here, this COG will move higher to this position, and it will be causing the tipping angle become lesser than the original. So that's why it's not it doesn't allow to having a tilting angle during tilting part line during lifting. So from this, we could say that the practical or the actual condition which could be happen, we could solve with our gut explanation from an engineering point of view. Or in other words, I will say that practical and engineering should work together to get a safer operation. But sometimes out there they are fighting each other. So when that's happened, it will stop them to find a safer and efficient methodology in lifting operation, and it will be no longer a healthy environment working in there, correct? So now let's continue. Back again, once we have calculated the tipping angle, then we now could check the requirement. What is the minimum tipping angle that allowed based on the condition during operation? For this case, I'm referring to ISO 4305 here. These are various minimum requirement of tipping angle shown in table 3. For example, if you want to do lifting with crawler crane and it will be traveling, you can use minimum tipping angle 5 degrees here. But if it's only slewing or rotating, then you can choose minimum tipping angle 4 degrees, like that. Even it is mentioned that its travel speed up to 0.1 meter per second, but it's very very small, so we can assume that there is no crane movement on there. So yeah, is there any question up until here? Any
No, for
question?
me it's clear.
Yep.
For me it's clear, Nas.
Thanks.
I don't know.
If no question, now we continue to the ground bearing pressure. So before we start into this, I'm gonna put disclaimer here to always use the software that has been approved by the manufacturer to calculate the ground bearing pressure, because they know their things, of course, and what is inside the crane. So for your own safety, I will recommend you to follow the manufacturer's ground bearing calculation, if any. But if don't, maybe you can calculate by yourself. So the one that I want to share here about ground bearing pressure is the basic how these things works. So that when you get into the software, it will be easier for you to understand and hopefully no input errors. So it could lead you to the better result. So here I put links in this table that contains ground bearing pressure from certain manufacturers. Some of them are free, like Tadano or T-Rex, maybe, yeah. And most of them, you need to buy the crane to get the software. So, but for preliminary study, maybe you could calculate it manually before you get into the detail, like that. So the first example is crane with outrigger. This sample I took from weight and COG calculation class. So let's say we have a mobile crane with outrigger here, and we have configure weight and COG of each item in this table, like the load itself, boom, car body, and the counterweight. Now we are going to find the ground bearing pressure of this crane during lifting. So first we need to find the total weight and the COG, correct? So for the total weight, we can just simply sum up all the item, PA plus PB plus PC plus PD, right? Then we got the 1,625 kilonewtons for the total weight. And then we calculate the COG by using this formula. Okay. The basics, how to get this formula we explain in weight and COG class. However, this formula is common we use in calculate COG for structure, and we have already got this from the high school actually. So if we want to calculate the COG in X direction, Then we input the weight of each items, PA, PB, PC, PD, and multiply them with the X coordinates of each items. So yeah.
Nelson,
Yeah.
excuse me for interrupting. No?
Yeah.
So our reference will be always the slewing point of the crane.
Yeah. Correct.
Okay.
Correct.
Thank you.
But for here, because this is a different cases I took from my real project, So I put the origin point, it's here because this crane will be used in the offshore project, which is will be located on the Jacob barge. And the purpose of this calculation is to get the outrigger forces and make some requirement if we need to make a strengthening on the Jacob barge. So I choose this origin point because I need to make it the same origin point with the Jacob barge. So yeah, actually, for me, it's better to having the origin point at the slew ring here, like that. But in this case, I put the origin point here. You correct, yes, it. But you got my point, right? For the reason.
Thank you, Nelson.
Okay. So yeah, for the XCOG, we got 5.35 meters here. Okay. And if we want to get the COG in Y direction, then we input the weight. We will use the same formula, and we input the weight of each items and multiply them with the Y coordinates. That's all. That's the difference between the X calculation and Y calculation. It's only the coordinates here. So, and if you want to get the COG in Z direction, you can use COG Z coordinates in the formula. But in this case, we will not use that to calculate the ground bearing pressure because the Z coordinate is more used to calculate the stability as the previous topic, like the tipping angle. So that's how to use this formula. But don't forget, you need to consistent to use the origin point, like I said before. So all your COGs should be measured from the origin point that you have decided at the beginning. You are free to choose wherever you are actually gonna. So as long as you are consistent using that in your calculation. So after we got the COG coordinates, now we plot the COG like here. 5.35 meters of COG X, and it is measured from the origin point. So the distance of COG to A is from the origin point, yeah. So the distance to the A to the point A here is 3.82 meters because we have the outrigger A located at 1.53 meters from the origin point. And the distance to the YCOG is 5.28 meters here. So yeah, that's our crane COG during the lifting operation. Just for information here, The boom slewing angle shown in this picture is indicative only. So you might see that the COG here is not in line with the boom here. That's because in this job I actually check the COG in each degrees of slewing angle, but in the drawing we shown on only one slewing angle, just to avoid confusion. So, and then I copied this picture from the actual drawing. So yeah, there is the COG. Now we find out the reaction of each outriggers. I am assuming that this crane is rigid for this calculation, meaning to say that the deflection of outrigger's frame will be ignored in this calculation, so that we could calculate this by using a determined static structure analysis. So first, same as previous I have mentioned to you. First, we will distribute the load to one pair of sides. Let's back to the previous slide. So first, we will distribute the load to one pair of sides. You can choose either it's the left or right, or the left or right here, or these sides. Okay, so in this case, I choose to distribute it to the left or right, so it will be like this. This is the first step for this calculation. So now, if I look at from this direction, then we could simplify the system, become determined static structure like this. This is the COG, or I will say P total. And this will be A plus D. And will be B plus C, correct? And this will be 3.82, and this will be 5.44, correct? And the total will be 3.82 plus 5.44, 9.26. Correct? Is it clear until here?
Yes, fine by me.
Okay. Now, so it will be like this. The P total we got is 1,625, and then we calculate by using the determinate static. So total moment at BC equals 0 to get the super reaction at AD here. So what's the moment force that appear on the BC? It will be a reaction of AD times 9.26 meters, the distance to BC from AD here, minus P total times 5.44 meters, the distance to BC. Then we got the joint reaction at AD equals to 954.64 kilonewton. Is it clear until here? Anyone get some doubt on this calculation? And okay.
Repeat this section.
Sorry?
Support reaction AD. Can you repeat
Yeah.
that?
So the support reaction AD, we calculate by using the determinate static, correct? Which is saying that total moment at the support equals 0. So if we want to calculate the support reaction at AD, then we will use the total moment at BC here equals 0. What the moment forces that can be caused in the at the BC at the point at BC? It will be RAD times 9.26 meters, the distance to the BC, minus P total times 5.44 meters, the distance the P total to the BC. Okay, then we move this to here.
Nelson,
Yep.
sorry, no?
Yes.
Aren't P total and RID same direction? Why is it in negative?
Yeah, the reaction AD, let's say it's upward, right? But the P total is
Yes, because if
sorry. So
in terms of moment,
yeah,
rotation are the
yes,
same, P total
yeah.
and RID.
No, it's a different RAD. It will be like this, correct? The rotation.
Okay,
And
okay, yes, BC is the reference. Okay, yes.
Yes, correct. So yeah,
If P total goes to BC, goes the other way. Yes, exactly.
correct,
Good.
correct. Yeah.
Okay.
So
Thank you, Nelson.
yeah. So there you go. We get the reaction at AD, and then we continue with the BC. Then we use the AD as a reference. MAD moment at AD equals 0. Then what's the moment forces that can be showing in the AD? It will be RBC times 9.26 here. So RBC times 926, the distance to the AD, minus P total times 3.82 meters, the distance to AD, the from the P total to AD here. So we got the total the reaction on BC is 670.36 kilonewton. And then we check the equilibrium to make sure that our reaction is correct. So RAD plus RBC minus P total, and then we got it's equals 0. Then the reaction are correct here. Now once we got the reaction for each side, then we can continue to distribute the reaction to each outriggers. So we back to the COG. So first we distribute it to one pair of side, right? And the load point now will be at here and here, which is 5.28 meters from the A and B. So if we look at this side, then we will have two different separate load, which is this A and this is D, and this is 8.3. And this is 5.28. 8.3 minus 5.28. And this will be 3.02. And this is the reaction we get for the AD. Now, if it's BC, this is B, this is C, it will be the same distance. This is 5.28, this is 3.02, and this is 8.3. But the load we will use here is a reaction from BC, like that. Is it clear until here?
Yes, so far so good for me.
Okay. So we can once we get the reaction from each side, then we can continue to distribute to the reaction to each outriggers. For reaction at point AD will be distribute to so yeah. So this is for reaction at point AD will be distributed to outrigger A and D, while the reaction at point BC will be distributed to the outrigger B and C. By same methodology, we can use it's determine static calculation. For example, for this BC, we've got the reaction for site BC sites is 670.36 kilonewton, correct? Now we want to distribute this reaction to the B and to the C, right? So we have 670.36 kilonewton, and we want to with the position it is located 5.28 from the B and 3.02 from the C, and the total is 8.3 meters with the same methodology we used. So if you want to get the reaction at B, then we use total moment at C equals 0. And what is the moment at joint C? They are RB times 8.3 meters, the distance to point C, minus the RBC times 3.02 meters. So we got reaction at B is 243.91 kilonewton here. Same with the reaction C, we use total moment at B equals 0 here. And then we get the RC times 8.3, the total, the distance to B, minus RBC times 5.28, the distance RBC to point B. So we get RC equals 426.45 kilonewtons. And then we check the equilibrium equals 0, then our calculation is for the reaction is correct. Now, once we've got the outrigger forces, right? We could check the ground bearing pressure now. It would be simply by using formula force divided by bearing area. Now, in this case, the size of the outrigger is 0.6 times 0.6 meters. And we put 100 millimeters thick of bearing pad underneath. So first, we need to find the effective bearing area, right? This is the effective length and the width. So the mechanism of load distribution is like this. The outrigger force will be distributed to the bearing pad here. And then the bearing pad will continue the pressure to the ground with a certain angle, like this. It depends on the material. So the effective area at the contact between bearing pad and the ground will become more bigger. So it will depends on the what is the material of the bearing pad and the thickness, right? So it doesn't matter if you have a bearing pad as wide as a football field. If the thickness is only 1 millimeters, then it will be no effect to the bearing pressure to the ground. As we can see in the table, I assume the bearing pad material in three different materials. And if we compare three of them, the bigger area belongs to concrete. So concrete is good in load distribution, especially for bearing, but it is less flexibility because it's weight. So once we get the effective area, then to calculate the ground bearing pressure, we can just divide the forces with the effective area. In this case, for steel bearing pad, we get 949.9 kilonewton per meter square. For wood material, we get 750.5. And for the concrete material, we get 187.6 kilonewton per square meter. So yeah, that's how we calculate the ground bearing pressure for the outriggers crane. Any question up until here?
It's clear for me.
Yeah. Yes, it.
So it is based on the material and also the dimension of the parts.
Specifically the thickness.
Thickness of the outriggers or the pads?
The pads, yes. If you use the pads, then it's a thickness of the pads.
Okay, that's what.
Yeah.
Okay, thank you.
Is there anything question? If no, we continue. And the next one is crane with a crawler. Yeah. For this type of crane, there are three types of ground bearing pressure that could be considered. First is ground bearing pressure due to the normal pressure. The second is ground bearing pressure due to moment forces on x-axis. And the third is ground bearing pressure due to the moment forces on y-axis. So to get these three things, we need to know the COG of the crane, and the calculation process is same as previous crane without triggers. We need to combine all the components, weight, and COG plus the load to lift. If the COG has offset to the x-axis and y-axis, then there will be moment forces appear on each axis, and the moment forces will give additional pressure to each tracks. Now, for example, we have crane COG as shown in the red dot here, and it has offset to y-axis about 2 meters, and to x-axis is about 1 meters here. And the total weight of crane and load to lift is 218.3 tons. Now we need to calculate the ground bearing pressure for this. First, we calculate the ground bearing pressure due to the normal pressure. For this, we could simply just divide the total load with the total area of the tracks, which is in this case is 1.2 times 8.1 and times 2, because we have 2 tracks. Then we get the total area for the track is 19.44 square meter. Then we divide the total load, which is 218.3 tons by the area. We got and then we get 11.23 tons per square meter. So that's for the normal ground bearing pressure. And then the next one is ground bearing pressure due to the moment on x-axis. As we know, the formula to calculate moment force is load times the offset measured from the origin axis. So if we want to calculate moment x, then we use the offset to y. This is the moment x, right? So if we have offset here, then the moment x will be causing by the offset to the x-axis. X-axis will be the center of the rotation. This is the center of the rotation. Then the offset that should be considered to make the moment at x direction will be this 1 meter. And for the moment y, let's see. For the moment y here, the center of the axis is this. The center of the rotation is this. Then the offset we use is this 2 meters. Okay. So for the moment, we got P total 218.3 tons times 1 meter. So it's 218.3 ton meters. Now, how we distribute this moment to the tracks? That's the question, correct? So we will use a section modulus of the track. Now, the question again, what is the section modulus? Section modulus is a geometric property of a section. In structural engineering, we use this to design a flexural member like a beam or even paddy. So basically, this calculation is same as if we want to design a paddy. The formula you can find in structural engineering books. First, you need to find the inertia here of the tracks. Then you can calculate the section modulus by divide the inertia by the distance to the center of the tracks from the axis. But for me, if the shape of the crawler for the cranes that you're gonna use is same like this, then I think you can just simplify by using this formula. So you only need to adjust the dimension B and H and A and D. So B is the length of the track here. And the H is 1.2 is the width of the track. So this is B, this is H. And the A is the total area of the tracks. So it will be 2 times B times H, like that. And the D is the distance from the center of the axis to the center of the tracks. Here. This is D. So yeah, I think it will be more simple if we just follow this the what is this
Nelson,
the
please.
formula. Yeah.
Sorry. The center of the axis.
Yes. Yes.
usually is the slewing
Yeah.
of the crane.
Yeah. Yeah.
To be clear.
Yes, correct. Yeah, for this case, yeah, I use the center of the slurring.
If we
This
use
is
another point, do we have the same results or the result will be different?
should
If we
be
choose to
same.
put for the
Should be same. Yeah.
okay.
Yeah.
So okay, thank you.
No problem. No problem. So yeah, if you use a different location of the origin point, it will be showing the same value for the ground bearing pressure. So no problem with that, but you need to make some modification on the calculation here. So yeah, just to suit the yes, right. So yeah, it will be the same result. So yeah, from me, I think would be better if the tracks has the same form, or yeah, if it's a shape of the crawler, you can just simplify it by using this formula. It will be not really much different. So yeah,
Nelson, please. Nelson,
yeah.
please. Sorry,
Yeah.
I am asking too much questions.
No problem, no problem.
For the d, small d, not d square. Okay.
D square, yeah.
Then d square. You have put 7.3 plus 1.2
divided by 2.
divided by 2. But
Yeah,
it is the distance from, you told us
center.
that's center of 7.3, not all 7.3, the center.
Yeah, it's from the center, right? So if we want to check,
Okay.
it will be like this, right?
Okay. Just do it. So the center to the center. Okay.
Yes,
Thank you,
yes.
Nelson.
Yeah,
Got
no
it.
problem, no problem. So yeah, so to get the ground bearing pressure because of the moment, then we can use the formula. Ground bearing pressure equals to is a moment divided by the section modulus. So for this case, we got the ground bearing pressure due to moment x is 2.63 ton per square meter. Now the question is how this ground bearing pressure distribute to the tracks. Now let's back to this slide again. If we look at the COG location, it will rotate this crane to this side, correct? Then that means this side will get more pressure than the other side, this side, correct? So I will put here as a positive, and this will be the negative. Okay, so that's for the ground bearing pressure due to the moment x. Now we continue. Is it clear up until here?
Is it clear, everyone? Aldo, Rajesh, Tarek, Yazid?
No, yes, it's clear for me. For me, it's clear.
Still okay, yeah?
Yes.
Okay.
If you have any question, just raise your hand. Or after that, after class finish, and you still have any question, also you can ask through our WhatsApp group or directly to Nelson.
Yeah. So
Chat, you can use the chat also.
yeah. Now we continue with the ground bearing pressure due to moment A. It is the same process as the moment X, but for this we need to change the section modulus. Again, we need to calculate the inertia first here, and then we continue with the section modulus. It will be confusing.
Nelson,
Yeah,
so not for everyone to be confused. This is my, not mx. It's a mistake or not? For the moment of
it's
the
oh,
y-axis,
sorry.
it's my. So
My.
to
Yeah,
not to
yeah,
be
yeah.
confused with the mx.
Yeah. So yeah, we continue. Yeah. Once we get the section modulus here, then we could calculate the ground bearing pressure by divide the moment y here divided by section modulus. So we
Uh,
got the ground bearing pressure is 16.7 ton per square meter.
Why
Yes,
didn't we
it's
add the Nelson in the
yeah,
inertia? Why didn't we add the A multiplied
AD.
by AD? Yes.
Yeah, because the y axis moment, the inertia of y axis. So if we look at here, the center, why we add AD square, because the center of this track based on the x axis is here. So the x axis is there is a distance from the center of the track to the x axis. This is D. Now, what if the center of the track to the y axis?
Yes, there isn't big. It's
Yeah, so
it's
it will be
it's
yeah.
already in the y-axis. Okay, understand. Yes.
Yes. So
Thank you,
the
Nelson. Thank you.
D is 0, correct? So that's why it's not appear in this formula. And then we calculate the section modulus, and then we got the ground bearing pressure. So it will be the same process with the moment X. We get 16.7 ton per square meter for the ground bearing pressure due to moment Y-axis. Now, how this ground bearing pressure gonna be distributed to the tracks? As we see, the COG, yeah, it is. As we see the COG is here, then it will be cause this crane will be rotating to this side, and then the bigger pressure, the front track will get more pressure here than this blue one, correct? So I will say this is the positive, and then this is the negative. Okay. Now we continue by combine the ground bearing pressure. First is the normal ground bearing pressure. I call it as GPP1. For this ground bearing pressure, all side of tracks will get the same pressure, right? So that's why I put here as positive at all position here. Okay. The second is ground bearing pressure due to the moment X. I call it as GBP2. As I have explained before, the moment direction of this moment will give pressure more to the tracks at Y positive. So it will give more pressure to this side. Correct. So at this side track, the track at this side will be, I will put plus GBP2 here. And the other side, it will be minus GBP2. Okay. And then we continue with the GBP3. That's the ground bearing pressure due to moment Y. So yeah, I call it as a GBP3. Look back at the COG location, and we know that it will rotate the crane to the front, right? So it will rotate to the here. Then the GBP3 at this side will giving more pressure. So that's why I put the GBP3 here as a positive, while the rear tracks is negative here. So we combine all together. At the rear, I get the minus 2.84 tons per square meter. This one. And for this one, I get minus 8.1 ton per square meter. And we go to the front, it's a 30.56 square meter. And the last one is a 25.3 tons per meter square. So if we look at the section A, section A is if we look at this track to this side, then we can see the ground bearing pressure like this. And if we look at from this side, the other side, section B, it will be like this. But why I put this as a 0? Because there is no ground bearing pressure minus. So when we get the negative ground bearing pressure, that means it started to losing the contact to the ground. So that's why I put it's as a 0. So yeah, I think that's all for the ground bearing pressure calculation for mobile crane. Any question regarding this?
Well, I have a question for difference between GBP2 and GBP3 are the same. Is why?
GBP2, GBP3. Which one you mean?
The one before, slide before this. The slide before
Oh yeah. This is the y-axis, and also this is the y-axis. I copy
Oh,
it.
okay.
Yeah, it's the same actually. No, just to
Well,
show you. Yeah.
which one is GBP1?
GBP1 is the normal pressure.
Normal pressure. That were the one we have
Correct.
calculated in the beginning. Okay,
Yes,
just
correct.
so.
This
And could you
one.
please repeat only, Nelson, positive and negative?
Oh,
I
sure,
got a
no
little bit
problem.
confused about this one.
Okay, no problem. So for to combine the ground bearing pressure, we should know the COG, correct? And the COG, if we have offset, then it will impact to which sides the crane will be rotating. So for this case, the COG is, we found it's on the X positive and Y positive. It's here. If the COG is here, then the moment X and X will be rotating, the crane will be rotating to this side, correct? And then if it's rotating to this side, then the most pressure will be got by this side of crane, correct? That's why I put here the GBP2 is on this side of crane of track is plus, and here is negative. That's because the rotating direction is giving more pressure to this the Y positive tracks. Now for the GBP3, it's because of the moment Y-axis. The moment Y-axis, because the COG is located here, it will rotate the cranes to this side, correct? If this tracks rotating to this side, then the more pressure will be got by this side. That's why I put here the GBP3 as a positive, while the rear tracks I put as a negative. And then we can combine them together. That's how I get these the total GBP at each side of the tracks.
I got
So
it. I
yeah,
got it.
yeah.
I got it. Thank you. Thank you, Nelson.
No problem, Yasin.
Since everyone is not asking questions, just I'm asking too many. Yeah. I hope no one is bothered by my questions.
No.
So you can help, no, to bring up more insight to our participant, right? Yes, it.
Yeah.
We like if our participant ask a question, so it will be more. It will give you more information.
Okay, that I will have another question then.
Yeah.
So Nelson, this is for only one angle, one side, because I remember in one project, one of the client asked me to give him the ground bearing pressure on each point. I mean, at least of the rotation of the crane. I mean, 4 points, 3 points, based on the slewing side of the crane. For example, if we have a telescopic crane, we have outriggers A, B, C, D. So he asked for each point, A and B and C and D.
Yep. So yeah, that's what the section showing here. So if you have this section, right, it will be the section A. I will say it as section A. Then we can get this section view, which is the rear of the tracks will have a 0 ton per square meter. Why I put here as a 0? Because when we get the negative pressure, actually there is no negative pressure.
Right.
So that's why it's negative. It's showing us that it will be started to lose the contact to the ground. So that's why I put as a 0 here.
Yes.
And
totally understandable.
Yeah, and then the front is 30.56 ton per square meter, and will be the same as the other tracks here. B, let's say it's a section B, and then it will be like this. So yeah, like that. Yes, it.
Okay. What about telescopic cranes, Nelson?
The telescopic crane is here. Yep.
So it is the reactions.
So the reaction is I didn't. So it's BC reaction at B is 243.91, and the C is 426.45. But I didn't mention here the reaction of A and D. If you want, we can calculate here. So yeah.
I mean, like we did in the crawler. I mean, point A, this is the GBP, point B, point C, point D.
Oh, you want to, so yeah, it's the same process as because I use the maximum load here, so.
Yes, that's why I told you, because I faced this problem with one of the clients. He asked for each point in the telescopic crane.
Okay. So yeah, it's the same process. Once you get the reaction from each outriggers, then you can divide it by the effective area
Okay.
based on what material you use for the bearing pad and what is the thickness, like that. It will be the same process.
Okay, so you
Yeah.
you put a reaction divided by the surface or the area,
Correct.
and you got
Yes.
your ground bearing pressure on
Ground.
that point.
Yes, correct. Yes.
Okay, perfect, perfect. Thank you, Nelson. So
No
far,
problem, Yasid.
you can be happy, guys. I don't have any questions.
No problem. I will be happier to help you.
I know. Thank you, Nelson. You have helped me a lot. Thank you.
No problem. So yeah, anything question?
Nelson,
Yes, Tarek.
please, about the negative GBP,
Yep.
that means that the force is reversed. Instead of the pressing down on the ground, the crane is generating an upward force.
Sorry, I don't get your point.
When the GBP is negative, that means that the force is reversed.
So yeah, for example, as I mentioned before, if we have the COG on here, then the moment will be the rotation direction of this crane will be here due to the moment X, correct? And the moment
the crane is generating an upward force.
Sorry?
In this case,
Yes, yes. For this case, I mean.
Yeah.
Yeah. So for this case, if we have the COG right here, then it will rotate the crane to this way because of the moment of X, correct? So if we have the rotation direction to here, then the most pressure will be got by this side of tracks. Correct? That's why so wait.
What I'm saying, that the crane is generating an upward force.
So wait, let me try again, yeah. So when we get
I think what he is trying to say is that since the results is in negative, meaning it's a reverse force. Usually the force will be from up the crane to the ground, but since it is negative, it's from the ground up.
No,
He
okay.
explained, Nelson explained this, Tarek, he said that negative meaning that the crane is losing contact. It's like there is no contact between the crane and the ground. That's why he put it 0.
There will be an
yes.
imbalance. Static
Yes. Yeah. So there is when we get the negative pressure, it means there will be no
a part of the crane, crawler crane, may lose contact with the ground. Nelson?
I think that Nelson lost internet connection.
Yes.
Now
Yes. Sorry?
we lost your connection few seconds before.
Hello?
Yeah, now
Yes, Tarek. Yeah, so yeah, if we get the negative ground bearing presence, that means we have zero contact to the contact pressure to the ground bearing to the ground between the tracks.
In this case, a part of the crane, crawler crane, may lose contact with the ground.
Yeah. So it will be started to tilting.
Exactly, yeah.
Yeah. Correct. So yeah, anything else? Before we continue with the capstone project. If no, we can continue with the capstone project. Let me explain some to the capstone project. So yeah, now I will give some explanation about the how the capstone project work. So so here we will treat the same as the real project, and we are trying to do is we want to build two ways communication between us, which is FDP and you. So because we are understand that by participating a class, doesn't matter how expensive you paid for that or how expert is the trainer, it will not make us the participant become an expert after that. However, the two-way communication, especially after class, or we can call that as after service, that way will help us to achieve our goals in our career. So that's why we have capstone here, and this capstone will not have points or whatever it is. So the points will be same for all participants. And you are free if you want to discuss with me or another trainer from FDP, not limited about this capstone, but also you can discuss about your project that you are running right now. Maybe you need a second opinion or anything else. So yeah. So in this project, we are going to lift a gas turbine from vessel to the yard. The weight of this gas turbine is 241 tons, as I highlighted at the table here. And this is the rigging design to calculate the rigging weight. And the goal is we need to lift this turbine to the yard, and you can choose either it's a single crane or double crane. But for information here, we will limit the UC maximum up to 80%. And you are free to choose whatever crane will be used as long as you have the crane data. And if you don't have any, you can just tell me so I could provide some cranes include the information. And that would be better if you could get the ground bearing pressure as well. So yeah, all the calculation you will put in the summary section, and the crane data or any references that you use in your calculation, you can put in the appendices section here. So yeah, any question about the capstone project? Or any question about anything?
Is it considered an inshore since it is
Well, if you ask me, I will consider it's an inshore. Yes, correct. Because it's we doing the lifting from the port or the
Port,
from the
exactly.
vessel to the yard.
Exactly, yes.
Yeah.
Okay. Let me just to check something.
So you free to choose what cranes you're gonna use for this project. Just treat this capstone project as your own project. So yeah, is there anything question about this capstone?
Any question, everyone, about your capstone? It's
For me, it's clear.
For me, all good.
Yes, Aldo, do you have any
All
question?
is clear.
No, so for me it's okay. So it's clear.
Rajesh, Freddy,
Clear.
clear? So
We received the study material 2 part only. Can I share the part number 3?
Part, which one? Sorry?
The last one.
This one?
No, the last one.
You mean the ground bearing pressure?
Yes. The calculation.
Wait. Which one? This one?
Yes.
Yeah. Yeah, Rajesh. What's the question?
which one do you wanna ask, Rajesh?
The pad thickness I will select on this one.
Sorry?
The pad, outer rigger pad.
Oh, outrigger pads. Yeah, this one?
Yes.
So the outrigger pad is 0.6 meters times by 6.6 meters, and the thickness is 100 millimeters. So yeah, what's the question about this?
Which part do you wanna ask, Rajesh?
The pad selection, madam. Outer rigger pad size selection. See.
Oh
0.
yeah, the size selection. So actually, it's you are free how to choose the size. It doesn't matter how big is your the pad size. The important thing here is the thickness and the material. So let's say it's a steel, correct? If it's steel and we have outrigger, the original outrigger here is 0.6 and the thickness is 100. If it's steel, then the effective area or the effective length, it's not longer 0.6 meters, but now it's B plus 6.6. The B is 0.6 plus 2 times 0.1. The 0.1 is the thickness. So that's how we got the width effective, or the B effective is 0.8 meters. And it will be the same with the length effective, correct? Because it's a square, 0.6 times 0.6. Now, if it's a wooden bearing pad, it will be a different distribute angle. So now, if we would, then we will use B plus 3 times of the thickness. So it will be 0.6 plus 3 times 0.1, and it will be 0.9 meters. Yeah, 0.9 meters, and it will be give a more bigger effective area. Now, if it's concrete, then it will be a different effective area also, because we will calculate it by 3 times the width, the original width. So it will be 3 times 0.6, and it will gives us 1.8 meter with effective width, and it will be same with the length of effective length. And then we get the effective area by multiply the width and the length effective. So that's how to choose what's the size of the bearing pad we will use. So if it's still 0.8 meters, then we will choose the bearing pad width is 0.6 0.8. So this is 0.8. If it's wood, then we will choose the dimension will be 0.9 meters. Here, 0.9, and so on with the concrete, like that, Rajesh. Is that clear for you?
Thank you, sir.
Is that clear?
Yes, thank you.
No problem. No problem. Is there anything else?
Dian, please, do we get the recording of both days?
Yeah. Dian will send you the recording.
Okay, thank you.
No problem. So yeah, that's for the crane stability. Maybe you have a question for the next project, or for your project or anything else. You can directly just send me a message or email, and I will reply it soon.
Okay, any other question? If not, we can close our training today.
Sir, I have one question.
Yeah, Fred.
Yes.
About the material of the matting board. How
Yeah.
if we use the composite matting board?
The composite bearing pad usually is manufactured by the one companies. Is it right? So
Yes.
if it's manufactured, then you will refers to their data. So I think it's they will mention it in the data sheet when you purchase their bearing pad.
Okay. Thank you, sir.
No problem.
Okay, so all participants, thank you so much for your time today. If you don't have any questions, so I will prepare our recording and I will send it to you, including with Google Form feedback. So please help us to improve our service for upskilling program. So we need feedback from you. What section that we have to improve, and then what is the next upskilling program that you need to learn, so we can try to prepare for you. And then also for your information, our program is more about upskilling. So that means that we are not focused to give you certificate, but we focus to give you skill. So it's like fill the gap between your certificate and then your expertise. So in our upskilling program, we focus to what I say, to sell our experience or best practice that we have from our subject matter expert. So many people ask like, what type of certificate that we get after your class. So I can say that we give you certificate of achievement if you finish your capstone project within 1 month. But if you cannot finish your capstone project, so we only give you certificate of compliance or attendance. This means that you don't get any credit, yeah, because if you finish your capstone, we will put notification that you pass your class. So we focus on upgrade your skill, your experience. So hopefully you can be more qualified than before you take our courses. And then in our program, we encourage you to build connection each other. Try to contact each other, to connect each other. We create WhatsApp group. Ask about information for job, information for the project, sharing knowledge. And I hope that this communication will bring not only technical benefit for you, but also networking. Because at the end, what you need for your job is not only technical, but also networking. So we will create one WhatsApp group, a big WhatsApp group from all the participants, and then you can connect each other. You can say hello each other, connect in LinkedIn each other, and sharing about all information that you need. Ask, because if you don't ask, people don't know about what you need, right? So this is very important. Hopefully, with this community, we will rise up our skill and also our networking. Because if you only connect in LinkedIn without direct in touch like this, so it can be like who is this person? But if you meet together in our program, you learn together, so it will be more create personal in touch, right? So hopefully you can connect each other, become a big family to achieve safe lifting operation. This is from me and Nelson. Thank you so much, Nelson, for your time today. And thank you so much for our participant that you trust with our program and you join with our program. So I wish you luck for your career, and then enjoy your capstone project. If you have any question, just direct message to Nelson. And then for next month, we will try to open the same courses like this, but also we add the new one for the heavy transport SPMT. So in SPMT, we will learn about the fundamental of transport operation. So you know how to calculate for the basic engineering for SPMT, and then transportation, yeah. Tipping point, you also learn tipping point for the transportation. So lifting operation, there is two, like use crane and also use SPMT. So if you want to learn about SPMT, I will send you detailed information about the new program that we will launch next month for English class, and then see you again. Thank you so much, everyone, and then have a great evening.